All right, we are now recording, and this is lecture for 6/22/2017. Welcome, everyone. Welcome, if you're joining us, welcome, everyone. This is us. Okay, now I'll start the video. Welcome, everyone. This is our 6/22 lecture. Here's the plans, the deep thoughts. I've wasted the time for deep thoughts. That'll come some other time. I want to finish this example. We're going to do Newton Euler. We're going to derive the Newton Euler formulation today. That's insightful in part in that it shows us the limitations, helps remind us how Newton Euler and how we'll use that. We're going to take a quick, very short break. I pushed us a little bit on time, short, but I want to start saying a few things about research each week since we're here, because that's why you're here. I mean, the classes are part of it, research. So I thought we could just have, start having a regular short break. The one thing I do want to say is maybe I can start meeting with you, or we could start having some here every week. Maybe I can start meeting and look at your labs, and help start connecting you to an early advisor. We'll say that during our break. Then we'll wrap up a few of my notes. Looking at Euler's rotational equations. That's really what's coming out today, is to introduce to you Euler's rotational equations, and then what I call Euler's angle equations. That gives us the complete set of 12 differential equations needed to solve a dynamics problem for a single rigid body. And then, of course, you just map that to as many rigid bodies as you want. I will wrap this up with an example, and then we'll leave just the last couple minutes to talk about plans next week, and then make sure I grab homeworks or discuss that on the way out. And of course, at any time, feel free to bring in discussion. Okay, so I'm flipping over. Any quick questions, comments on things before I jump into this example? All right, here's our example from last time. This example is terrific in that it pulls together these ideas of writing particle, we need to do the particle kinematics, describing the motion, both displacement and orientation for bodies, defining the velocity, acceleration. So my drawing's not the best here, but I think we started that, and I think everyone saw we have this first cylinder on a rotational axis moving, rotating around the N3 by theta 1. Off the side, it has a bar or a rod with a disc rotating around this axis that here I labeled B1. With an intermediate frame we called A, the frame A. Let me mention something quickly that I didn't do when we were laying this out. I always have to have an inertial frame. And typically in setting these up, I'm going to add, well, when I say frame, I mean a coordinate frame. That's what I'm looking for, this idea of a coordinate frame. I always have an inertial frame. I always have a frame attached to my body. And then I can add intermediate frames as convenient. Typically, I will add one intermediate frame for every degree of freedom. So I'll have, for every degree of freedom, I'll add an additional frame. You might think in this case that then it would also imply that there would be multiple bodies. So if I think of my multi-body system, that's what we're here about, is multi-body dynamics. I think about my multi-body system as one that consists of links and joints being kinematic pairs, connections between the bodies. The simplest joint is going to be a 1 degree of freedom joint. I'll try to treat the world that way. So I will have a frame associated at each kinematic pair that gives the rotation of the next body to the previous body. So let's look at that specifically in this example. In this example, I've got my frame. I don't want to go too far from my speaker, but in this example, I've got my frame right up here, my inertial frame, and that'll be attached to ground. Then I've got this cylinder. You can see this big cylinder here, this vertical cylinder. It's rotating relative to ground. So I've attached a frame to the cylinder. That's my A frame. I could have given another name. I just chose A. Then off the side of the cylinder, there's this little bar, and there's a disc spinning. Here there's a disc off that bar, and that disc is another body, right? The kinematic pair is this revolute joint, and so I've attached a B frame to that body. So that's conceptually what I'm going to do. I could just keep adding bodies, and I'll keep adding frames. Together, we did look at the rotations. We described the rotations between those bodies, and this was an important practice point for the work that we've done so far, which is describing orientation. So I said, well, I would like to have a description of the orientation of body A or frame A, which is attached to the cylinder, back to the inertial frame, and then a description of the orientation of body B, the disc. That's really what I'm interested in this problem, back to the inertial frame. So, you know, I listed both of those. So for body A, for the rotation A projected back onto N, I saw it was simply a rotation around the Z-axis or the N3 axis by theta 1. So I constructed it easily. For the rotation that projects frame B onto frame N, well, in this case, I saw that it was a combination of rotations. It was first a rotation around the 3 axis, then a rotation around the new 1 axis. Does everyone see that? It was first a rotation around the original 3 axis. Notice it was the rotation around the N3 or the A3. But they always stay aligned. Then it was followed by a rotation around the A1 or the B1 axis. That's a current axis rotation, what I've been calling the Euler rotation. That means I post-multiply my operations. So I had first the rotation around the 3 axis, followed by a rotation around the 1 axis. I multiplied the 2, and that gave me that rotation operator. Okay, so that's the method. I could, you know, at this point, I think if I break the idea down into single degree of freedom rotations, we could do an example stacking up 6 of these, multiplying them through. The process would be the same. Okay, so I've got those 2 rotations. Now let's go back and revisit what we're trying to solve. So I have my description of point P. I called that R relative to my inertial frame. So I started up here. So I first had a vector negative H in the N3 plus L in the A1 plus little r in the B3. That's how I described that R. Any questions on that? Pretty straightforward. I could have written it other ways, but that's how I wrote it. Then I took the derivative. I noticed that, you know, this was, you know, some of these terms just went to 0. Now I dropped lots of terms that went to 0, and I end up with these 2. The angular velocity of A with respect to N crossed with this L in the A1 direction, plus the angular velocity of B with respect to N crossed with R in the B3. So I need the angular velocity of A with respect to N and I need the angular velocity of B with respect to N. Correct? That's what came from that equation. Yes, I need those 2. We talked about those a little. Let me add an extra word. Angular velocities are vectors. Everything is a vector except for orientation that we're going to see kinematically. Angular velocities are vectors, so I can add vectors. You know, I can add vectors together. So it's fairly straightforward to write the angular velocity. I didn't make that clear, so let's do it in this example. So the angular velocity of A with respect to N, that's just a rotation around the 3 axis, either the N3 or the A3 by theta 1 dot. That one's straightforward. So it's theta 1 dot around the N3 or the A3. Now, I'm going to choose the A3 direction here. And let me give a little foreshadowing. Let's look up at the equation I need. I need to cross omega A with respect to N with L in the A1 direction. I could have written theta or omega A to N in the A frame or the N frame. I chose the A frame. Why? Because there's my other vectors in the A frame. If I do the cross, they have to be in the same frame, right? That's one of the big reasons I'm going to use the rotation. When I do these operations, the vectors is obvious, but let me say it anyhow. The vectors all must be in the same frame. This one was an easy choice, so I'm just going to keep it right in the A frame. At the moment, I've got so many choices. I'm not going to even delineate them all now, but that's what I'll do. Now, the angular velocity of B with respect to N. Let's look up at our figure here. So I need the angular velocity of frame B that's attached to my spinning disk out here with respect to N. And notice it's 2 components, right? It's first the rotation around the 3 axis by theta 1. And then there's also a rotation around the A1 or the B1 axis by theta 2. And the angular velocities are linear, so I can just add those things up with no loss of generality. I mean, I can just do that. So I get theta 1 dot A3, and then I've got that theta 2 dot, and it was around the B1 or the A1 axis, A1 or B1. Doesn't matter, or B1, they're the same direction. So when I look at the cross product, I'm going to cross that thing with a vector in the B frame. So I'm going to go ahead and use my B1 axis. So now I'm ready to do the cross product, right? Vector omega A to N, I got to cross to something in the A. B to N, I got to cross to something in the B. So I'm going to put this thing all in the B frame coordinates. So I need to write omega B to N in B frame coordinates. How will I do that? It's partially in B frame coordinates, right? But not completely in B frame coordinates. Yes. So I need to pre-multiply by the rotation operator. This is already in B frame coordinates. I need to project this part of the vector, this term, into B frame coordinates. So I'm going to rewrite this as the rotation that projects from, what rotation do I need to write here? Kevin, you're being an overachiever today. So, all right, Kevin, give it to us. I'll continue. I want to go from A to B. Well, just give me this easy one right now. What would be the one you'd like to have? And I'll just write it down. You want a projection from where to where? Well, you already said it. You want to project from A to B. That's what I want. So I'm just going to say I want that rotation operator times the theta 1 dot A3. Then plus, I don't need to project anything. You know, this guy's already in B, so I'll leave it in B. All right. Now, Kevin, you were trying to, in your head quickly, under pressure, say, well, what is this A to B? So let's just write down a little equation and get it from there. So we said that the rotation, let's see, we have a bunch of rotations, but we said that the rotation from B to N is the rotation from A to N times the rotation from B to A, right? We had that here. So just wrote it down again. And we know that the rotation of A to B is just the inverse of the rotation from B to A. Oops, that's the inverse. Is my writing legible enough? Do I need to take a little more care? Okay, you just kind of start giving me an evil eye if I need to clean that up a little. And the inverse is, Kevin, hate to wear you out, but the inverse of a rotation operator. Oh, man. Okay, a rotation is the transpose, because this is a special set of matrices. Now, I don't want to, I mean, you know this, but I'm trying to say obvious things. Those things. Not all matrices inverse of transpose. If I just had to make up what percentage, I'm just making 0.1%. I mean, if I randomly generated, well, I guess it'd be less. We use rotations a lot, so you see them often. So don't expect that. It's only going to be for the special case. All right. So if I put that back in here and get the transpose, so finally, I need to solve for the, well, let's do the steps. Give a little detail this time. In the future, we'll do it more quickly. So there's my projection from B to A transpose. That's the guy I want. Here's my equation. So what do I need to do to solve this matrix equation? Well, they've already done that, even in review. I pre-multiply both sides by the inverse of my projection from A to N. So my next equation is going to be the inverse of the projection of A to N times the projection of B to N is, you know, the A to N inverse. Okay, and that just goes to identity. That, of course, is the transpose. And I already have the projection of A to N, and I have the projection of B to N, so I can stick them in there, and then that will give me you know, the transpose of this guy, or I could take the transpose, you know, I can take the transpose of both sides, right? I could also do that. I'm doing a bunch of operations here. Gosh, if I don't stop doing this, I'll get, we'll never get done. But allow me to do one more matrix operation. Matrix operations are very important, obviously. So we're taking a little time. Is everyone okay on the operations I've done this far? Getting there. Okay. Yeah. Yes, I know. Yes. Okay. Yeah, I know. I thought I was just going to show you this one line and then we'd see it obviously, and then I've got hung up. So bad me in this case. But at this point, I feel compelled to finish. So the last step, since I brought it up, here I'm practicing, I guess this is the one time I'm going to practice some matrix operations. So now I want to take the transpose of both sides. So B to A transpose, R A to N, that one's transpose times R B to N. I'll take the transpose of that whole thing. And so the last thing, the transpose of the transpose is just back to the original matrix. Now, quick reminder, what's the transpose of this product here? What's the transpose of a product of matrices? Do you recall that? It's not simply the transpose of each term. Reverse the order. It's the transpose of the reverse order. So this will give me R B to N transpose R A to N transpose, and those will just go away. Okay, so there I've got a nice clean equation from the two things I already have, and I practiced, we just practiced two steps in this derivation. Maybe you catch up on that. We're just going to throw all this away. So if I've got a string of, matrices multiplied, I take the transpose of that group. I've got to just take the transpose of the inverse order. Effectively, I guess you could probably derive it fairly easily, although it's not coming straight to my mind, but I'm assuming you're just sort of undoing a process. You probably would invert and then multiply. You could probably back that out. Okay. Now, after going down that rabbit hole, or we could just by inspection say, well, what is the projection of B onto A? Or A onto B, right? It's a rotation. The projection of B onto A is a rotation around the one axis. I should have just done that, right? We'll all agree I should have just done that. So I could just say, well, or it's just projection of A onto B. Let's just write it the other way because we've been projecting from the outer frame back. So R B onto A is simply a rotation around the one axis, which I already wrote. I even already wrote it. So don't ever solve the problem the way I was just doing it, okay? At this point, I'm not even going to try to justify it. So there I have the rotation, and then here's the transpose, or here's, yeah, this is really better. Yeah, my bad. Now I owe you 10 minutes. Take the transpose, so it's 1, 0, 0, 0, 0, cosine theta 2, sine theta 2, negative sine theta 2, cos theta 2. That's the guy I need. So I'll go back to my omega B with respect to N. It is this A projected on the B times the theta 1 dot A3. So I've got my effect, an A3 term, the A3 term gets multiplied by the third column. So I'll have the A1 term will get multiplied by the first column, A2 gets multiplied by the second column, A3 gets multiplied by the third column. So I know I just have 0 times theta 1 dot in the B1, sine theta 2 times theta 1 dot in the B2, cosine theta 2 times theta 1 dot in the B3. Just walk through that multiplication. So it was sine theta 2, theta 1 dot in the B2, plus cosine theta 2, theta 1 dot in the B3, plus theta 2 dot in the B1. So there we go. I've got my B1, B2, B3. Now I need to cross omega A with respect to n crossed with, was it L in the A1? And I needed this omega B with respect to n crossed with R in the B3, I think it was. All right, so this will be pretty straightforward. So I get a theta 1 dot up here, a theta 1 dot A3 crossed an LA1. So a 3 cross a 1 is a positive 2. So I get a positive theta 1 dot L in the A2 direction plus, well, plus then this guy. I get a 1 cross a 3 is a negative R theta 2 dot B2. I get a 2 cross the 3, that's a positive R sine theta 2 theta 1 dot in the B1. And then I get a 3 cross a 3, which is 0. So there's my velocity.
So, I'm sorry, can you step back on that?
On that cross product?
Yes.
Okay.
So
let me do the cross. Let me spell out the cross product for this term here briefly. I was doing too many steps and now I'm doing not enough. So sorry about that, Preston. So I got theta 2 dot cosine, or excuse me. So I got two vectors crossed with each other. The R vector was 0, 0, R, and that was in the B frame. And the omega was theta 2 dot sine theta 2 theta 1 dot cosine theta 2 theta 1 dot. Okay. Then I cross term by term. So there's only the B3 term. So theta 2 dot from the B1 cross the B3. So we get a B1 cross the B3. In this case, I'm doing my triangle, but the negative B2 term. Right, R theta 2 dot and the negative B2. I get a sine theta 2 theta 1 dot in the B2, so I get a B2 cross the B3. B2 cross B3 is a B1 positive. So I get a sine theta 2 theta 1 dot R. And then finally, I have a B3 crossed with a B3. And any vector crossed with itself is 0. So, good. And then the first one, I did the same thing. It just had the one term. Good with that? Yeah, Jason. Yes. Okay, so notice now this isn't just a mixture of terms, all right? You know, let's take a second and talk about that. That's going to be the nature of these problems. I've added frames. Why? Well, at the moment, because I said, hey, let's add the frames. But practically, that's going to be the way that I recommend you deal with these problems. The downside is now I've got terms described in different ways. Right? How did I end up with these terms? I chose it by convenience. I chose, well, what are the least number of operations this far, thus far, okay? Is that a valid description for V? Absolutely. It's in mixed frames. But that is the total velocity of V. I can write it in any frame I wish along the way. And I'll just, at the moment, since I'm doing it for convenience, I'll continue to do that. All right. Now, quickly speaking, what are a couple thoughts on convenience? Now I'm going to take the derivative. I'm going to work with a vector. I need to take one more derivative because I actually asked for the acceleration quickly. So I'll probably just work with this vector. We'll look at that. But a couple comments, you know, practically speaking, when I'm done, it probably would make sense to have them in all a single frame. And probably the frames that make the most sense would be the body fixed frame or the inertial frame. I will be doing my, we're going to see in just a moment that I'll be doing my dynamics. I'm going to want to express the motions, the velocity, the accelerations and velocities in the body fixed frame. There's a reason for that. So typically I'll use the body fixed frame. If I'm trying to look at the results later on, I'll do it in the inertial frame. But again, there's convenience. it's somewhat justifying the middle. The last comment I want to make, Jason. I do have one more thing to say, right? When we took the derivatives, you'll see that in a moment. Remember I said we could take the derivatives. We always have to take the derivatives with respect to what frame, Kevin? For dynamics.
The inertial frame.
Inertial frame, right? We always have, that's the place that these things are going. So we're taking the derivative in the inertial frame. Look, this is described in different coordinates, A, B. Does that mean I took the derivatives in the A frame or B frame coordinates? No, it means I'm expressing it in this coordinate. I was very careful that when I do the derivatives to always take it with respect to the inertial frame. But when we do that, you know, if I'm taking the derivative, I'm taking it with respect to the inertial frame. When I take the derivative of this guy, we're going to see that in a moment, that's not in the inertial frame. That's in the A frame. So I've got to apply the transport thing. So I'll take first the derivative of this guy plus, you know, this guy, you know, plus the angular velocity guy. Or excuse me, that transport thing, the angular velocity cross with that. Or I could express the thing entirely in the end frame coordinates and then just take the derivative of the components. Transport thing will go away. But I'm going to choose not to do that. I'm going to choose to stick with this guy. All right, now we're ready to go to the next step. And I'm going to jump back up to my initial equation to make it uniform. Okay, so I'm going to jump back up here. Yeah. Okay, so I guess I was just reviewing how we got here. So we took one derivative and we got this equation. So you know what, I'm trying to be general, probably to the point of getting too general. So let's just start here. Okay, let's just pick up here. Jason, you asked about mixing the coordinates or converting, and it's really your choice as you go through. I don't know that I'm making the right choice, but I'm just going to stick with this set. All right, so there's my velocity, and that's the velocity point P. I guess I'll add that notation now. Now I need the acceleration of P. I'm going to get it now by taking a second derivative of R or the first derivative of my velocity of P, since I have it here. I think since I'm sitting right here, I'll take that. And again, at the moment, Jason, probably just so I can show the most steps possible to practice, I'm going to leave it in this coordinate frame. All right, so work with me, Jason. So I got to take the derivative of each term, right? So the derivative of the first term, the theta dot L, that's going to be theta 1 double dot, correct? Because it is a variable, LA2 plus theta 1 dot times the derivative of L. L is constant, so I'll just leave that 0. Am I done? No, I also need to take the derivative of the A2, basically the direction. And that's going to be the angular velocity of frame A with respect to frame N crossed with this term, theta 1 dot LA2. So that's the first term.
Say that one more time.
Yep. Oh, I started adding P for some reason. I think I'll just, this is of P. Okay, press one more time. Theta double dot L, okay, derivative first, times the rest, plus the derivative of this thing times the rest, that was 0.
Right.
And then finally, the derivative of the direction times the vector. And that's the transport theorem. So the derivative of direction is the angular velocity of this direction, omega A crossed with the direction, plus you got to carry these, so you bring them back. The angular velocity of A times that.
All right, we get to practice 2 more times. Let's go to the next term. The next term is this negative r theta 2 dot b2. R is constant, so I'll get negative r theta 2 double dot in the b2 plus the derivative of the direction, which is going to be the angular velocity of b with respect to n crossed with negative r theta 2 dot b2. And then my last term, same thing, plus r, well, not quite the same thing. Now I've got 3 terms, don't I?
I've got 4 terms here, right? That one's constant. Sine theta 2 is not constant. Theta 1 not constant. B1 not constant. So I've got to do the derivative.
All right, so let's just, we're here, we're stuck, can't get out. So r, let me just start through the derivative of sine theta 2, that's theta 2 dot times the cosine of theta 2 times theta 1 dot times b1 plus, but now I've got a smile on my face, plus r times sine theta 2 times the derivative of the next term, that's a theta 1 double dot b1. And then the third term is the derivative of the b1, so it's omega beta n crossed with this vector r sine theta 2 theta 1 dot b1. That's my acceleration. Lots of terms. I've got to simplify that some, but that's what is that? That's my acceleration. Yeah. It's painful. Okay, let's look at this for another minute. I think I'm going to. I hate to do this, but we might call that good at the moment. Let's look at a couple. I got a smile on my face because we get a couple terms here. We get theta double dot, right? The regular acceleration term. We get these. Let's see what kind of here. Well, we get theta double dot terms. We've got it here and here, but I can see it already. I'm going to get some intermediate cross terms. Look, I got a theta 1 dot term and a theta 2 dot term. And I'm actually going to get a bunch of them. They'll show up here as well. But I'm getting these cross terms. These are Coriolis terms. I'll probably get some theta 1 dot squared, some theta 2 dot squared. All those terms are going to naturally show up inside this. To complete this problem, I'm so over time, I'm going to stop at the moment. Maybe I should probably work this out and post it. To complete this problem, now I just have to collect the terms. I just have to do the work. I've already got the good news is I've already got the angular velocities. Right? So it's not have to do cross product. I already have an established product. Yeah, I think that was in the 3 direction. I've got that angular velocity. I've got this angular velocity. Just cross it. The exact same thing that I did before. And then I can do the cross here. You know, I might just combine these. I might just write down here's the angular b with respect to n. I could just say, well, this is the vector of crossing, so I get b1 times b2. Pull those together. I'll get all of those. I'll write them out. Some will be in the A frame, some will be in the B frame. And at that point, I'll choose, well, at any point along the way, choose to change the frame. I guess in this problem, since I've done this point, then I would probably choose to put it on the B frame so that 3 multiplied each frame by the rotation. All right. With your blessing, well, I say that with your blessing, I'm going to leave this example. I'm going to call this one done. It's not even close to done. I'm going to call it done. You see the process? So, you know, when we were deriving the rotation, I'm not quite sure what in your mind, what was going on in your mind, how you use it. There are many ways you can use it, but here's one way. We're going to use it in these problems continuously because we're in these mixed frames. Now, one last time, you might say, is there another way? Well, there's always other ways. You could take and write all the motion in the inertial frame immediately, but to do that, you're going to need to use a rotation, and then just take derivatives in that frame. That way is okay. I'm actually practicing this because I think this is a skill that probably you've practiced less. So that's why I will typically do those. You know, in terms of operations, is one faster than the other? It just depends on the problem. I don't know that one is necessarily better than the other. I tend to use this more, but it's kind of your call. All right, questions on this? Comments? All right, then I will now move. Well, it's embarrassing how far we've gotten. I'm going to now move to our next thing, which is be what I have planned for the lecture for today. And that is the Newton Euler equations of motion. Newton Euler equations of motion. Oh my. We are recording. Yes, we are recording. Thank you. I have, you know, as all the methods so far, I've got on the website, I've got the little snippets, you know, little 5-10 minute breakdowns of each topic, but I'm going to go through, I'm just going to march through those here as well. So we had said fundamentally that Newton, you know, Newton derived Newton's equations. They were the method in such a clean form that that's what we use to describe really the world around us. We talked about the limitations, you know, the extents and the limitations and the like. Newton wrote those for really particles. You know, I think they were thinking of celestial bodies, you know, stars and moons and satellites and the like. But it applied to particles, things that reasonably could be treated as point masses. Euler came along and extended that concept to rigid bodies. So we're going to look at both of these. We're going to do a derivation of these in why, so we can understand underneath, you know, really look under the hood, I guess I'll say, to use a cliche, of how these are derived. And it'll help us think about what frame we're going to work in. All right, so I'm going to draw a rigid body out here, just a general body. My body has, I'm going to have an inertially fixed frame, a frame N back here. I'll just at this point call it N. The N has an origin at D. And out on my rigid body, I've got a center of mass G. So that's my little symbol for center mass. Typically, I'll call the body center mass G. It's pretty typical. Center mass, center of gravity. We kind of use them interchangeably. Actually, I use them exchangeably. Are they exchangeable? Well, as long as your gravitational field is constant, then yeah, that's fine. If your gravitational field varies in some way, or I suppose if a mass field, which I don't even know what it is, so we'll just leave it. If a gravitational field varies, then the center mass and the center of gravity might not be aligned. The only applications I can think of are space applications. You get gravity gradients, you stabilize. But you have to have a big body. You have to have a big spacecraft. Like the International Space Station would be an example, where it is large enough that the gravity varies slightly over that. So the center of mass and center of gravity don't combine. Other than that, I can't think of practical examples. So we'll just treat them the same. On this body, I've got a little particle. The particle is particle P. That particle has is going to be located relative to the center of mass with some r, some little r vector. That particle has little mass dm. Its sides are little length dr. It's just my little particle. I've got a vector going out to the center of mass, which I'll call dg. And in this case, my body is going to be acted on by a gravitational field, if I like, g. Oh, and that, actually, the thing that I do want to include is that in the body, there's a body fixed frame B. Okay, that's a little bit of a busy figure, but you get the basic idea. The idea is I've got a body that has center of mass, and there's a point on a particle on the body with some infinitesimally small a little dp. It's got mass dm and the like. So the first thing I want to do is, what's that? It's my first page. I'll make sure I stay in order. Well, Yeah, okay, so the first thing I want to do is say that my, first thing I want to do is write my Newton's equation. So my Newton's equation for that particle would say the force on that particle, and it's a little particle, a little differential particle, so I'll have a differential force on it, is the acceleration of that particle times dm. And then the total force here would be the integral of df over the body, which would be the integral, I have to integrate both sides, AP dm. I'm not sure I dropped that in the notes here. And let's look at the right-hand side first. So my integral of P, right here. Sorry, my subscripts are getting a little weak. And so I'm going to leave it here. So I'm going to integrate over the body. I'm going to leave it here. So it's going to give me, I'm going to get, if I integrate about this, you're going to see these terms in a moment. So that's going to give me the,
Why is that with your energy forces all over the body? But then you're saying acceleration D in the minus, not acceleration.
yeah, thank you. I need, well, no, I got to integrate over all, I'm going to do this over the entire body.
Right. But acceleration.
Yeah, so my acceleration is going to be, well, yeah, so it's acceleration of PDM. So I'm going to get these couple terms. I'm going to get the dg plus, so I've got to do the second derivative of this thing. So I've got to get the second derivative of this thing. So I'm going to get dg plus, you know, my terms r double dot. No, you're fine. R double, okay, actually. Okay, let me just sketch this out very briefly. I'm going to get the r double dot term. I'm going to get the alpha cross r. I'm going to get the 2r dot omega dot term, and I'll get the omega cross r term. Okay. What you're going to see is that, and so this is the second derivative of this guy. So I'll just put a double dot over that. What you're going to see is that we're going to see, I'm going to skip these steps, but if you go through this, you're going to find that if point G is defined as the center mass, I'm going to get integrals of r dm over the body. By definition, an integral of r dm is 0 if you take it about the center mass. That's going to drive all these terms to 0, and so I'll get that the force on the body is the acceleration of G times the total mass of the body. And I guess at this point, I've got enough, we're going to see each of those steps here in a moment, so I don't want to jump into them at the moment. You're going to see that. The point that I want to bring out is that on the right-hand side, you get AG, acceleration of the center of mass, that's a vector. And on the left-hand side, you get the force, and this is the sum of forces. This is the sum of forces acting on the body, and we're considering external forces only. So yes, when I'm looking at the little particle, it is, I'm just looking at the mass of the little particle. All right, let me move to the next one. I'm going too deep in that guy, but I'm going to go deep into the next one. So the next step I want to do is now look at the moments. So I'm going to look at the moments acting on the body, where M here's my moment. And I'm going to sum moments about for this part, I'm going to sum moments about D, okay? And now I'm using a slightly different guy here, but by definition, a moment is R cross F And I should say, let me make this R prime cross F. So it's a different R than the R I've shown above. So just by definition, moments is R cross F. All right. So my little moment, so to get the moment about D, I'm going to integrate all the moments acting on each particle. And here I'm going to put a sub D, meaning it's about D, okay? So I'm going to integrate the, make this a nice square M. The moments on all the particles, on all my little particles over the body. And these, I'm going to take these moments about D. So that means I need to integrate my left-hand side. So on my left-hand side, my R is going to be a vector going from D to P. And I've got to cross it with, you know, the term that I have above. So we're actually going to see where all these terms go in just a moment. It's going to be I'm going to cross it with the acceleration of P times dm. So effectively, I've got R cross df. So dm is R cross df. I'm going to do that over the body. So I'll probably stop writing the integrals over the body. So the sum of moments on the left-hand side, this is going to be, you know, I sum all the moments, and these are the external moments. I'm going to get on the left-hand side the sum of moments acting about D, sum of moments acting about D, and these are external. And on the right-hand side, I'm going to start expanding. So I get the integral of dp. So dp is going to consist of two terms. It's dg plus the little r that I just showed, crossed with, and now I'm writing the terms that we looked at just a moment ago. AP is going to consist of two terms. When I take the derivative of AP, I'll get first, it's the acceleration of g, which is what I called that dg double dot above, plus, now I've got a couple terms. I've got r double dot in the r hat direction plus alpha cross r plus omega cross r, and finally 2 omega cross, need to cheat here, r dot r hat. Now, if I assume a rigid body, which is what we're doing at the moment, well, at the moment, for the majority of this class, that means that my R is constant. Wherever I am, the R is constant, right? So R double dot is 0, R dot is 0 for a rigid body. If you want to go back and take this class with elastic properties, you go back and redraw this term. So that gives me now the integral of, so that leaves me then just these three terms for my acceleration. What I want to do now is multiply through. So my next line I'm going to do as follows. I'm going to start multiplying through, and I'll drop those out. So I first get dg crossed with ag, and everything here is dm. That's my first term, plus the integral of dg crossed with, the r double dot term goes away, so I get crossed with alpha cross r dm, plus the integral of dg crossed with omega cross r dm. And for the remainder of this work, I'm not being careful with my parentheses. You know, in theory, I could do the cross operations in any order, but I'm going to assume I'm always going from the right to left, right? You might say omega cross omega is 0, but it's got to be parentheses. So I'm giving you a little warning. I'm going to be semi-careful with my parentheses. These parentheses need to stay there. In our case, we're writing them down. At the moment, well, just keep that in mind. I guess I'll try to write the parentheses. Plus the integral of r crossed with ag dm, plus the integral of r crossed with alpha cross r dm, plus the integral of r crossed with omega crossed with omega crossed r dm. Whew, okay. Equals to sum of MD. So I'll just, yes. I'm just going to bring MD down each time, the sum of the external moments. Those, that's important. Thank you. Plus. That's what you were saying. Plus. That's very important. All right, now let's look at, let's expand this out a little bit. The first term is dg cross ag dm. dg is independent of the body, so I can pull it out. It doesn't change as I integrate over the body. ag doesn't change as I integrate over the body. So I get the integral of dm, which is just the mass. So there I can see I get dg cross ag. That one's pretty straightforward, times the mass. Second term. The second term gives me, look, I got this integration. dg is independent of, if I integrate over the body, it does not depend on that. Alpha is independent of little r. So I can pull the dg and alpha g out for the second term. So I get dg crossed with alpha, these are all vectors, crossed with the integral of r dm. All right, now I'm starting to get to the point where I'm throwing some of these out that I skipped above, but we would see. The integral of r dm is what? If I'm integrating, and notice here, I'm integrating about point G. But, yeah, I'm integrating at the centroid. So by definition, the integral of r dm about the centroid goes to 0. The centroid is chosen as that point in which the integral of r dm goes to 0. That's how it's chosen. So anytime I get an integral of r dm, that's going to go to 0 because G is the center of mass. All right, let's go to the next term. Well, we're on a roll here. dg crossed with omega I can pull out, crossed with omega I can pull out, crossed with integral of r dm, and you know my parentheses would be like that. Once again, the integral of r dm goes to 0. Okay, so the integral of r dm is going to 0 because by definition, and I'm pulling out these other things. Constant. They're constant for the body. Constant for the rigid body. Plus, the next term I've got r cross agdm. Well, I can swap the order of the cross product by changing the sign. The dot product I can swap the order. Sign doesn't change. But the cross product, I can swap the order, change the sign. So I'm going to make the next term minus ag crossed with now the integral of r dm because the r has to stay in the integral. So, man, maybe this isn't going to be so bad. That goes to 0. I'm on a roll. And then I've got the last two terms. And I'm going to, in my notes here, call it A plus B, where this is A and this is B. So my sum of moments is this dg cross mag. I guess we could just say that this is the mass of the body. This just goes to the mass of the body. Those terms all go to 0. Then I get these last two. So we now need to explore these. So this is where the fun begins. All right. So now let's look at A, term A. The integral of r cross alpha cross r dm equals. All right. I don't know if this is how Euler did this. I have no idea. I mean, this is, I see this stuff and it's like, well, I have no problem rederiving it when someone showed me how. I always wonder, you know, I guess they just, without Twitter, I guess they didn't have time to wait. They weren't wasting their time sending tweets or whatever. They're just bored, I guess. So anyhow, we'll just assume I'm just making all this up. But, you know, Euler's sitting there, he's saying, I wonder what this thing is. And he says, well, why don't I try the triple vector product? You all recall the triple vector product. Okay. Yeah. Oh, yeah. You know, his wife's downstairs says, you know, Euler, are you coming down for dinner? Wait, I'm in the middle of the triple vector product. Anyhow, triple vector product. Yeah. You know, I call it the back minus cab rule. Back minus cab rule, which is to say that A crossed with B crossed with C. I mean, it is amazing. I mean, it is amazing. These guys figure this stuff out. But hey, we're working on stuff. So the back minus cab rule says that A cross B cross C is vector B times, this is a times here, A dot C minus vector C times vector A dot B. Okay, that's the rule. So I just wrote down the triple vector product for your enjoyment. And Euler, I guess, had the great idea, well, wait a second. I've got an A cross a B cross a C. So first, let's let A equal R, B equal alpha, and C equal R. And so, we get this integral of now alpha times R dotted with R, right? A dot C, yes. And then there's a dm minus, I'm just writing down both terms, minus the integral of C, which is R times A dot B. So that's R dotted with alpha. And I can write the terms in either order. Yeah. Okay. So we got to this point. So now this is my A. So my A is this. And then we're going to expand this out a little bit. Well, what is this thing? I don't know. He might have stopped for the day. He says, what do I have now? This is meaningless. And he went home and did whatever. And then he came back the next day refreshed. He said, well, I wonder what happens if I expand this out. So let's let R equal X in the B1. And this is important, right? R is described, this is important. He's describing the local frame, right? I mean, we kind of showed it that way. So it's X in the B1 plus Y in the B2 plus Z in the B3. And let's let alpha vector be, I guess I'll just call alpha 1 or alpha X. Notice my 1s and X's kind of merge. Alpha 2 in the B2 plus alpha 3 in the B3. So he said, well, I've got nothing to do today, so let's expand this out. So I get, again, the integral of alpha times R dot R. So I get alpha 1 in the B1 plus alpha 2 in the B2 plus alpha 3 in the B3 times R dotted with R. X squared plus Y squared plus Z squared. Okay, that's the first term, right? And then, bracket here, minus, now I got this thing. So let's see, my R is X B1 plus Y B2 plus Z B3 times R dot alpha. So that's X alpha 1 plus Y alpha 2 plus Z alpha 3. I mean, this is the only explanation. They had nothing else to do, so they just kept at it. I say it's the only explanation. I mean, it's a great discovery. It's what we do, right? We sit and work on things. Most of the time they don't work out. So he did that. And then he expanded on the B coordinates, all right? So if we pull the B coordinates out, so the first term, I'm going to write down all my B1 terms. Then write down all my B2 terms. Then write down all my B3 terms. So let's see my B1 terms. So this first guy, I've got a B1 term. So an alpha B1, so I pulled the B1 out. So alpha 1 times X squared plus Y squared plus Z squared. And then I get a minus X squared alpha 1 minus XY alpha 2 minus XZ alpha 3. Should have left a little more room there. Okay. The next term is alpha 2 times, the x squared y squared plus z squared minus yx alpha 1 minus y squared alpha 2 minus yz alpha 3. And then finally, alpha 3 times that magnitude minus zx alpha 1 minus zy alpha 2 minus z squared alpha 3. Okay, did that. And then, okay, we're almost there actually. He didn't know it, but we do. We know what he ended up with. Now, make this a matrix times alpha 1, alpha 2, alpha 3, and these are in the B direction, okay? So I've got these terms. So if we pull out the alpha 1 terms, let's look at that. Yeah, exactly. Watch this. We got alpha 1 x squared minus alpha 1 x squared. Just exactly. So watch this. Okay, and if we move across, the coefficient of that B1 component and alpha times alpha 2 is minus xy. And then the coefficient of the alpha 3 is minus xz. All right, next row. The alpha 1 term is a minus, well, it's again a minus yx or a minus xy. The coefficient of the alpha 2 term is this minus y squared plus x squared plus z squared. So I guess it's x squared plus z squared. And then the third term would be minus, zy or yz. And then the last row is alpha 1 is minus xz. Alpha 2 is kind of hard to read my writing there, but that's minus yz. Oops. Yeah, that's good. And then x squared plus y squared. Excellent. Okay. And notice that this guy is in the B frame, right? So it's the B1, B2, B3 coordinates. All right. We're on to something now. I honestly don't know the origin of the, I guess we got to contribute this to Euler. We got to this, right? What is that thing? SO3. No, it is not SO3. It is not. This is the inertia matrix. This is the inertia matrix. This is the I. I'll say the inertia matrix. Oh, you know what? Sort of skipped something there. Almost. There was an integral out front of this whole thing. dm. And I can pull the dm in. Okay, so actually the integral of this matrix dm is the inertia matrix. All right. That is the inertia matrix or the inertia tensor, call it what you want. The integral of this whole thing dm. That's what I'm talking about. All right. We know the inertia matrix. We've seen the components. We just looked at the components, but where did it derive? Where did it come? It came here. Let's move back up for just a moment because it's easy to loop. Well, I'm sure we've lost the forest for the trees. Let's back up. So we were talking about this term, this R crossed with alpha crossed RDM. That gives us, that yielded, I don't know if you caught it, but that yields I alpha. Matrix I times alpha. That's what that yields. Because the I is all that stuff, and then there was an alpha. That's how we get I alpha. So this is the derivation of the inertia matrix. I want to say a few quick words. I'm so tight on time. Let's come back and talk about the, I do have a little time to talk about the inertia matrix. We'll come back and talk about it, okay? But that's the inertia matrix. I will say, you're familiar with this, you get these
These terms, we actually call the modes of inertia, and these terms we call the products of inertia. So those are called the inertia matrix. You can see these squared distances, which we've already did a practice on what these are the products of inertia. If you have a matrix that's just diagonal, use zero, but product of inertia go to zero, we call that the principal inertia. They become principal inertias. And we'll write down a few things. Okay, so let the fun continue.
Good time to stop the recording.
It is probably a good time to stop the recording.